first thing we did was the so-called method of washers. Right? Method of washers. So, right, you have some sort of object, right? You have some object. You are rotating that object about an axis, right? So you take that object, you rotate it about an axis, and you get some what's called a solid revolution, right? So the line goes up with x, right? And you get the volume. Can anybody tell me the formula for the volume of this object? Using the method of washers. Do you remember how you do it? You cut at a particular at each time x, you cut through at each position x, you cut through your object, right? And so the volume is going to be the integral from a to b of the area of the cross section, right? A of x is the area of the cross section. The area of the cross section dx, right? You get these, you sum these disks, you sum the volumes of disks, and then you take them all together, and that's your total volume, right? And in the case of something like this, getting the area of the cross section is easy, right? Because it's going to be what? It's going to be a circle, right? So the area is pi r squared, where r is your f, right? So you get this pi f squared dx. Okay, right. So that's the method of disks, or the method of washers if you have two functions, right? If I've got also an inner function, right? If I've got an inner function and I'm going to pull out that inner object, so my solid is just the big object minus the little object, right? Then I'm going to have, right? In that case, the volume would be the integral from a to b of what? Somebody tell it to me. Jake?
It would be pi big R squared.
Mm-hmm. Pi big R squared.
Minus pi little r squared.
Minus pi little r squared. And I'm just going to combine them together as pi big R squared minus little r squared. D. Okay. Right. And so this is the method of disks. This is the method of washers. Right. Okay. So. Okay, there's another method called the method of shells. Okay, and that is let me draw a picture. It's like this. So suppose you have some object like this. Okay. Suppose you have some object like this, and you're going to rotate it around the y-axis. Okay, see this like this, right? You get this. You get the solid obtained by rotating this thing around. Okay, so if we are going to do this by washers, then basically what we're doing is we're taking this. It's basically like you're cutting this thing up into horizontal pieces, and then rotating those horizontal pieces around, right? And that gives you the washer, right? Well, the method of shells is you cut in the opposite direction. So you cut instead of cutting perpendicular to the axis of rotation, you cut parallel to the axis of rotation. Okay, so slice parallel to the axis of rotation. Okay, you slice parallel to the axis of rotation. So let's call this guy our upper function of x and our lower function of x. upper function of x, lower function of x. And then you have some tiny width here, dx. Okay. And then you say, okay, well, what would be, if I take this thing and I rotate it around, I get a cylinder, right? I get basically a cylinder minus a smaller cylinder, right? You guys see that? I get the cylinder, but I subtract off a smaller cylinder from inside, and I get, just this what's called a cylindrical shell. So really, these are cylindrical. People always just say method of shells, but it's really these cylindrical shells. Okay. Okay. So so what's going to be the volume of the shell? What's the volume of the shell? What would be the volume of the shell? Think about it for 1 minute and see if you can tell me. So say that we're taking this slice here at point x. Okay. Let's think about it this way. What's the height of this cylinder? What's the height? Well, if this is x, the y value here is going to be u of x, right? The lower value is L of x, right? So what's the height here? U of x minus L of x, right? The height is going to be the upper guy minus the lower guy, right? Okay. What's the radius of the cylinder? X, right? The radius of the cylinder is x, right? So what's the circumference then? What's the circumference of the circle? Thanks. 2 pi x, right? So the circumference here is 2 pi x, right? So if I took this shell and I unrolled it, right? I took the shell and I unrolled it, and I take the shell and I unroll it, right? I'm going to get this rectangle, right? And the height of the rectangle, you've got some height and you've got some length here. The length is 2 pi x. Right? So the area of this thing is going to be 2 pi x. Right? So this is height. So you get 2 pi x. Area is going to be 2 pi x times the height, which is the upper guy, minus the lower guy. Right? And then you have this thickness, this dx thickness. So there's some infinitesimal thickness that we're calling dx. And so that times the dx is the volume of that infinitesimal shell. Right. So what's the what's going to be the volume? What's going to be the volume of this object? Well, it'll be, if this is let's say 0 and this is b, then the volume is going to be the integral from 0 to b of 2 pi x upper guy minus lower guy dx. Does that make sense? That makes sense, right? So I'll draw it again. Right. The first way we calculated the volume was by taking horizontal slices. Right. Horizontal slices. What that's equivalent to is saying that we're going to cut our. This is the thing that we're rotating around, right? And we're going to cut it into. Tiny horizontal rectangles, right? And we rotate each of those rectangles around. We get a washer. We take the volumes of those washers, and then we add them up together, right? That was the method of washers. You've taken your object and you've broken it up into. You take the thing that you're going to rotate. You break it up like this, right? And then you rotate all those things around and you sum them together. Okay. Method of shells is very similar to that, right? It's just that we're going to break our object up like this, right? We're going to break our object up like this. We're going to take vertical rectangles and rotate them around, right? And so the volume of each of those rectangles is this, and then we add up all the volumes and we get the total volume. Okay. Let's do a concrete example. Let's put some numbers on this, okay, to make it more concrete. Okay. So just the picture that I've been drawing here. Suppose you have y equals the square root of x, and you also have y equals x squared. Y equals square root of x, y equals x squared. Okay, so just to wake yourselves up, take 1 minute and do it by washers. So give an integral that expresses the volume, but use the method of washers. Okay. Use the method of washers. Okay. Just to remind yourselves of what we were doing last time.
Rotate around y? Is that right?
Yeah, I'm sorry, rotate it around the y-axis. I should have said that. Okay, turn to somebody nearby and tell them what integral you put down. Don't evaluate it. Just write down the integral. Okay, so you think, okay, well, I want to get this volume, right? I'm going to use the method of washers. So, you know, for each y, I've got this thing, and I'm rotating it around, right? I'm rotating it around, I get this washer, right? For each fixed y, I think, you know, for each fixed y, I'm going to get a different washer, right? What's the area? What's the area? Well, it's going to be pi of the bigger radius squared minus pi of the little radius squared, right? And the radius changes with y, right? Okay. Well, what's the big radius? What's the big radius? Well, you say, okay, look, the big radius is going to be my x value here, right? The big radius is my x value. Y equals x squared, so x is the square root of y, right? So I get pi big radius squared, right, minus pi little radius squared. Well, here, what's the x value? Well, the x value is y squared, right? So pi y squared. Right? So that's the area. That's the area at height y. Okay? Right? So you get the area at height y, right? Area at height y, pi this guy squared minus that guy squared, right? dy, that's the thickness, and I'm going to integrate that between y goes from 0 up to y equals 1, right? From 0 to 1. Right? Is that okay? Right? Okay, so now we're going to do it. Let's do that again with the method of shells. So here we have the same sort of thing. Now we think, okay, now I'm going to chop this up along the x-axis, right? I'm going to chop this thing up along the x-axis, right? Well, for a fixed x, right, this guy is y equals x squared. This guy is y equals the square root of x, right? Well, what's the height of my object? That's going to be my y value, right? Right. The height at time x is my y value up here. What's my y value up here? Square root of x, right? Square root of x minus the lower value, the lower y value. Well, that's x squared. Okay. So I take that thing and I rotate it around, right? I rotate that thing around, and so when I do that, I get 2 pi times the radius. Well, the radius is x, right? 2 pi x times that height, and I have this thickness, right? So this is the circumference. This is the height, and this is what we're calling the infinitesimal thickness, right? And that gives us the volume of that cylindrical shell, and you integrate that between, well, x ranges from 0 to 1. Okay. X ranges from 0 to 1. You look at the range of x. Yes, Ray.
Why are we using circumference then? Why are we using circumference?
Because we need the volume of the cylindrical shell, right? Well, how do you get the volume of the cylindrical shell? One way to think about it is that if you cut it and then rolled it out, you would get a rectangle, right? You'd get a rectangle, and the thickness would be, you'd have a thickness of dx, okay? The height would still be the height, but when you roll it out, how long is it when you roll it out? Well, it's the circumference of this circumference of the top, 2 pi times the radius. Okay, so you get 2 pi x hx dx. Okay. Everybody okay with that? Any questions? Let me have you do an example. You try one. Okay. So it's along the same lines. Okay. Not too different. The line y equals x, and the same parabola, y equals x squared, and rotate that around the y-axis. Okay. So actually we did this example the other day with washers. This was the parabolic nose minus the cone, right? But you could also do it using the method of cylindrical shells. You all seem kind of tired today. Are you tired? Are you all tired? You all are tired. My God. Do you have a 3-year-old daughter who wakes up 3 times every night and comes and finds you, and then you have to put her back to bed? You have to sit next to her for like half an hour? You don't? Then I have no sympathy. Yeah, my daughter is very attached to me. It's good, but it's bad. It's good. Okay, turn to somebody nearby. Help with them, please. Okay, let's do it. So actually in my notes, I noticed that the problem's a little bit different. So let me make this 2x. Okay, it doesn't make that much of a difference, right? So the point is going to be 2 comma 4 rather than 1 comma 1. It's okay. It's okay. Perfectionists.
Yeah.
Okay, so what do you get? So what's the integral? Somebody would like to tell me? Tell me Anyone want to tell me about it? Or I'll choose somebody at random. Tanima, it is you.
So I didn't add in the 2x part. Actually,
That's all right, that's all right.
Actually, we were thinking the integral from.
So first off,
What is it?
am I dx or dy? Am I slicing with this? Do I fix my x and slice, or do I fix a y and slice?
Yeah.
X, right? So we're gonna have this thing. We fix an x. We take a slice there, and we're gonna rotate that thing around.
Yeah. So from, I guess.
Okay. So you say, what's the height?
Oh, the height
Yeah.
would be like the two functions, like x squared minus 2x.
X squared minus
Or
2x.
Yeah, right?
Not quite. No,
Oh.
x squared is the lower guy. 2x is the upper guy. Right. So you want the
Oh, sorry.
2x minus.
2x minus.
Yes. The 2x minus x squared. Right. Okay. So the volume is going to be the integral from what to what?
-2 to 2.
So it's actually not from -2 to 2, but from 0 to 2. From 0
Oh,
to
0
2.
to 2.
Yeah, if I took from -2 to 2, what would I get? No, you wouldn't get 0 actually. You would simply get double the original volume. Right? Right? Because you would get 2 pi. Oh, no, I guess you would get 0. I guess you would get 0 because your x would go, you'd have this x here, and then it would turn into 0. No, you would get 0. So yeah, it's rather you just look at your object. You look at your object here, the thing that you're rotating, right? The thing goes from 0 to 2. Okay, so from 0 to 2, 2 pi x times 2x minus x squared dx. Okay. Everybody all right with that? One more easy one, and then we'll do a trickier one. So let's take the same thing. But this time rotated this way. Okay. This time we rotate it around the x-axis. Okay. And again, I'd like you could do this by washers, but I'd like you to do it by shells. Okay, so again, this guy, upper guy is y equals 2x, the lower guy is y equals x squared. Okay. Right. Point of intersection is, of course, 2, 4. You take that same object and you rotate it around the y-axis.
You say the y or the x?
I'm sorry, the x-axis, excuse me. Yeah. Okay, turn to somebody around you. Talk with them. Okay, who would like to tell me how to do it? Elizabeth, go ahead.
I took the integral from 0 to 4.
0 to 4, right? So, right, we're going to slice with respect to y, right? So then the y's range from 0 to 4. So you get integral from 0 to 4.
And I said that was equal to, or inside is 2 pi y.
2 pi y, right? Because we take this guy and we rotate it around, right? Take this guy, rotate it around. Well, the radius is y, right? The radius is y.
And then multiplied by root y minus y over 2.
Root y minus y over 2.
That's my upper and lower.
Okay. In this case, it would be your right guy and your left guy,
Yeah.
right? So you want the height of the cylinder, right? So you take the x value here minus the x value here, right? 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 You want this width, right? You want this width at time y, right? So you say, okay, well, my x value over here is, this is y, so my x value here is the square root of y, right? Because we know that y equals x squared, right? And my x value over here, my left x value, right? I have y equals 2x, so x must be y over 2, right? So you get the guy on the right minus the guy on the left, and that gives you the width, right? So the guy on the right minus the guy on the left gives you the width, and then you multiply by the thickness, right? That gives you the volume of the infinitesimal shell, and then you add them all together. Okay. Sorry. Do you have a question?
No.
No?
Well, I mean, I'm just confused on how, like, it's the left minus, it's the right minus the left.
The right minus the left, because you want to figure out this length here, right? This length is the what we were calling the height earlier of the shell, right? Well, how do you figure out this length? It's going to be the number on the right minus the number on the left, right? If I say, if this is 2 and this is 3, what's the length here? Well, it's 3 minus 2, right? The one on the right minus the one on the left, right? This is because the people who made the number line were right-handed or something like that, right? Yeah, so things get bigger as you go to the right for some reason, some arbitrary reason. Okay. Other questions? Other questions? Okay, let's do a trickier one, which is the butt cake one that we put up last time. So you have this thing, y equals 3x minus x squared, and we're going to rotate that thing around the line x equals minus 1. Okay, rotate that guy around the line x equals minus 1. And let's do it by method of shells. Let's do it by method of shells. Okay, so remember that this was the same thing as x3 minus x, which meant that we intersected at 0 and 3. Okay, talk with somebody nearby.
I'm not sure. For the radius of the correct. The radius
Okay, let's talk. So, right, we're doing this by method of shells, right? So we're going to cut vertically. That is, we're going to fix x values, right? We're going to fix an x value and slice with that line at value x, right? We take that thing and we rotate it around. We get this. This shell. Okay. What's the height of the shell? Right. So we have 2 pi radius height dx. Right. This is the formula. Right, between 2 values a and b. Okay. Well, what's the height at time x? What's the height?
3x minus x squared.
3x minus x squared. Right. What's the radius? Don't blurt it out, but somebody raise your hand. Maddie?
X plus 1.
X plus 1, right? X plus 1 because we're rotating around x equals -1, right? So it's not x, but it's x plus 1, right? Make sense? Do it?
Why is it x plus 1?
Yeah. Thanks. I guess my radar is not far off today. Usually I have no sense of whether people understand or don't understand. Okay. Yeah, so the radius is, right, we take this guy and we're rotating it around the line x equals -1. We're not rotating around the line x equals 0 this time, right? We're rotating around x equals -1. So what's the radius here? Well, it's going to be x minus 1, right? The guy on the right minus the guy on the left, right? X minus 1, in other words, x plus 1, right? This is x, this is negative 1, right? The distance between them is the guy on the right minus the guy on the left, right? So you get x plus 1, right? Right, or, it's the absolute value, anyway. Right, so you get that. And what are A and B? What are A and B? X ranges from 0 to 3. From 0 to 3. Right? From 0 to 3. A equals 0, B equals 3. Okay. Does that make sense? Right? We're rotating this object, right? This object x goes from 0 to 3, right? We're rotating that guy around and we get this thing. Okay. Okay. That's about as tricky as these things get. I mean, there could be more. Maybe it's more complicated, but that's about it. Okay. Just for amusement, let's think about the problem. Whoops, that's not right. Let's think about if we tried to do this using the method of washers. Okay. If we use the method of washers, well, then we're going to fix a height y, right? And we're going to take this thing, right? And we're going to rotate it around, right? So we would need the integral between something and something, pi big radius squared minus pi little radius squared dy. Right? Okay, so we would need to get the big radius, and we need to get the little radius. Okay, and this thing was y equals 3x minus x squared. Okay. Okay. Goes from 0 to 3. And we'd also have to figure out what the y values range between, right? But you can do that, right? You know that the vertex of a parabola is in the middle, is in the midpoint, right? The vertex of the parabola is between the two roots, right? And so you just evaluate here, and it turns out to be 9/4. Right, so A is 0, and B is 9/4. Okay. Now, how would you get the radii? How would you get the radii? If this is y, we need to figure out the x values, right? We need to figure out the x values. Well, what are the x values? You can use, you want to figure out what the x values are, right? So what are the x values? If this is y, what are the x values? Some people are saying 0. That's strange. What are the x values? Well, you know that x squared minus 3x plus y is equal to 0. Right? So what are the x values? What x satisfy this? You can figure out using, say, the quadratic formula. You use the quadratic formula. So you know that x is going to be, 3 plus or minus the square root of b squared minus 4y, everything over 2. Right? Those are the y values, right? If your y is this, then those are your x values. Right? Yes? Yes? Okay. So you would get the guy on the right, right? The guy on the right would be 3 plus that thing over 2. the guy on the left would be 3 minus, right? 3 minus that thing over 2, right? Okay. And then the radius, the big radius would be the x value plus 1, right? Because you're rotating around the line x equals -1 again, right? So you get this thing, the x value plus 1. So the big radius would be this thing plus 1, and the little radius would be this guy plus 1. Right? Little radius would be the guy on the left plus 1. Right? And then you would put that into here and figure it out. Okay. So as you see, it'd be kind of awful. Right? It'd be awful, and you see that it'd be much better to do this one using the method of shells. Okay, so sometimes, one method is easier than the other. Okay, I'll let you go here.